Our last video discussed evaporation. This video is going to talk about what needs to occur for something to boil. Well, you're probably thinking, duh, put the water in the pot, stick it on the stove, turn it on, and wait. Okay, but why does that boil? And if we did that on the top of Mount Everest versus at our house at sea level in Florida, would it boil at the same temperature? What if we boiled it in a vacuum pump? We just happen to have a vacuum pump, so obviously we're going to try and do that. Before we discuss boiling though, let's discuss the concept of vapor pressure. If I had a closed container, so I'm going to draw a bottle. Don't hold your breath for my amazing drawings. And this bottle has water in it. And I'm going to draw some as molecules and some as not. Okay, there's the surface of my water. Now, we know that the high kinetic energy molecules are going to start to evaporate. So they evaporate, and now they're up above here, flying around, obeying the kinetic theory, bouncing off the sides of the container, bouncing off each other in elastic collisions. They're very, very far apart. Their size is negligible compared to the space that they're in. Now, eventually you're going to have an equilibrium reached. And an equilibrium reached will be when the rate of evaporation equals the rate of condensation. Because eventually there's going to be so many molecules up here, some of them are going to not have enough kinetic energy to stay in the gas phase, and they're going to go back in to the liquid phase. So you have this forward and back going on. Picture molecules leaving through evaporation, picture molecules coming back to the liquid in the form of condensation. And when evaporation equals condensation, you have a certain quantity of pressure being exerted on the sides of the container. And that amount of pressure is called vapor pressure. Oh, it's the pressure of the vapor. Now, if you were to look at the vapor pressure of water, water has a vapor pressure of about 0.61, whereas something like ethanol has a vapor pressure of 1.03. So let's think about this. Water has a vapor pressure of 0.61. Now, if I were to make water boil, I would have to therefore, so this is water, this is ethanol, I would have to put in a lot more heat into the water to get it to boil than I would have to put into the ethanol. Ethanol has a lower boiling point. Water has a higher boiling point. So why is that? Well, water has a naturally lower vapor pressure than ethanol, so therefore I've got to put in more heat energy to get water to a certain point. That takes us to our definition of boiling. The definition of boiling is when vapor pressure is equal to atmospheric pressure, something will boil. So if I have ethanol and its pressure, its vapor pressure is already at or near atmospheric pressure, I only have to add a little more kinetic energy in the form of heat by increasing its temperature to get it to boil. Whereas water, I have to add a lot more heat. So water has a higher boiling point, ethanol has a lower boiling point. And I'm going to show this to you and explain it again in the form of a demonstration in the next video. So what do you need to remember? Remember, the lower the vapor pressure, you've got to add more heat, the higher the boiling point. The higher the vapor pressure, the lower the boiling point. So let's talk about a liquid at sea level, and let's talk about a liquid up high. Let's put the liquid on top of Mount Everest. Okay? So we have two liquids. We've got this liquid sitting at sea level. The atmospheric pressure at sea level is 1 atmosphere, or 101.3 kilopascals. And then we've got a container of water. We hiked up Mount Everest. I don't know if you saw on the news how crowded Mount Everest got last season. Now this is at a super high altitude, sorry. So the atmosphere is thinner and the pressure from the atmosphere is a whopping low 34 kilopascals. Okay, so now I want you to boil your water. So I'm going to put some water in this one, put some water in this one. Now remember, what's the definition of boiling? The definition of boiling is when vapor pressure equals atmospheric pressure, we have boiling. Which one is going to boil first? The one at the lower atmospheric pressure or the one at the higher atmospheric pressure? Well, which one is closest to getting there already? Well, the one up on Mount Everest. We're only going to have to add a very little bit of heat to this to get its vapor pressure to become 34.0 kilopascals. And when we can add enough heat to make the vapor pressure equal to the atmospheric pressure, we're going to have boiling. And this is the crazy thing, folks. On Mount Everest, water will boil at 70 degrees Celsius. Okay, what about at sea level? Well, I've got to make my water boil, but I've got to bring it to a much higher vapor pressure. I've got to get it to match the vapor pressure of the atmosphere, and the atmospheric pressure at sea level is much higher than it is on Mount Everest. So I've got to get it up to a vapor pressure of 101.3. So I'm going to have to add a whole lot of heat, and it definitely isn't going to boil at 70 degrees Celsius. And you know from experience that at sea level, it's going to boil at 100 degrees Celsius. So the definition of boiling is when vapor pressure equals atmospheric pressure, we have boiling. If we take something up to the top of a mountain, or if we remove some atmospheric pressure by using a vacuum pump, which you're going to see in the next video, we can actually lower the boiling point. We can actually get the boiling point to lower so much that you can stick your finger in it and you won't burn yourself. So does that mean it would cook an egg? What do you think? Watch the next video and find out.